Hello, in this video I will be reviewing Calculus 1. So the first thing I'll be reviewing is piecewise functions. So for this question, we're trying to find g of f of x. So this. So the first thing I'm gonna do is basically in g, wherever I see x, I'm just gonna write f. So like this. Okay. So the next step is to basically solve these inequalities. So we want to see when is f less than 0. So x squared is never going to be less than 0 because it's always greater or equal to 0. So we're just left with x plus 1. F of x equals x plus 1 when x is less than or equal to 1. So we need to see when is x plus 1 less than 0, and also x has to be less than or equal to 1. So this gives us x less than negative 1, x less than or equal to 1. So we basically have to find the intersection of these two sets, which in this case is just x less than negative 1, because when x is less than negative 1, it is also going to be less than or equal to 1. So that's the first part of our inequality finished. So f less than 0 is the same as x less than negative 1. So now we need to find the f greater or equal to 0. So how does that happen? Well, x squared is always greater or equal to 0. So when x is greater than 1. And then we can do the same thing we did before here. We want to see when x plus 1 is greater than or equal to 0, but also x has to be less than or equal to 1. So this gives us x has to be greater or equal to negative 1. Just subtract 1 on both sides. And x has to be less than or equal to 1. So basically we have to do the intersection of these two sets, and so we get this range of negative 1 to 1. Because if x is less than negative 1, then it's not greater than or equal to negative 1. But if it's greater than 1, then it's not less than or equal to 1. So then we have this where it's equal to f cubed when f is less than 0, we said is the same thing as x less than negative 1. And then f greater or equal to 0, we said is the same as, well, it's equal to root f when x is, well, negative 1 is less than or equal to x, which is less than or equal to 1. So once you're here, we need to start looking at these two. So for f cubed, when x is less than negative 1, we have to look at what f is. So when f is less than negative 1, then obviously f of x will be in this branch, and in this piece, because when x is less than -1, it's definitely less than or equal to 1. So it's x plus 1. So we're just going to have x plus 1 cubed. Yeah, because f is x plus 1 when x is less than -1. So now we just have to look at this range. X is ranging from -1 to 1. So from -1 to 1, it will just be equal to So what I forgot here is that it's actually the intersection of this and this. Right, we want to see when is f greater than or equal to 0. It's greater than or equal to 0 when x is greater than 1, or when x is in this range of -1 to 1 inclusive. So we can just change this. We don't need this, right? Because the intersection, the union of these sets is what we need to see when f is greater than or equal to 0, which is just going to be, if you look at the union of this and let's write this as -1 to 1 union with 1 to infinity, then you're just going to get -1 to infinity. So basically x has to be greater than or equal to -1. So for -1 to to 1, it'll be x plus 1. In terms of from -1, so yeah, -1 to 1 inclusive. It will be just square root x plus 1, and it will be square root of x squared when x is greater than 1. And this is actually the absolute value of x, but because x is greater than 1, then that's just going to be x. So that's it. We have our g of f of x. And we can sketch this quickly. X when x is greater than 1, so say this is 1 over here. So if we plug 1 into x, then you just get 1, right? And then it'll just continue like this. We have square root x plus 1 when x is in that range. So we know that here it's going to be 0, right? And then we're just going to have like square root function, and square root of 2 is like 1.4, so put that here. So this is going to be inclusive, and this is just going to sort of go like, well, we also know that this is going to, square root of 1 is 1, so that's here, like this, right? And when x is less than -1, it's x plus 1 cubed. Okay. So if we were to sketch x plus 1 cubed without any conditions, it would have a root at -1. That would be its only root. And we know it's going to go from like quadrant 3 to quadrant 1, because it has a positive leading coefficient of 1, and it's power 3. Yeah, we know that there should be just the one x-axis, and it's going to be a point of inflection because it's order 3 root, so should look something like this. So then we can just sketch that onto here, and yeah, it should be something like this. I would redraw this real quick. Something like this. So let's see how good our drawing is. I just put f of x and g of x here and here. So g of f of x looks like this. This is around 1.4, right? This is our 0, 1 point that we have over here. And yeah, this graph looks pretty good, I would say. Yeah, so I guess, yeah, like this more accurately looks like this. So this actually has a looks a little bit more like this. But other than that, I would say this is pretty good. So moving on, I wanted to quickly mention punctured interval. So the idea is that it's important to understand the idea of an interval that surrounds a point with some radius. We can call it delta. In general, these two symbols are used a lot in calculus 1. This is delta, and this is that's just 3. This is epsilon. So the idea is you can have a punctured interval of radius delta around A looks like this. So x is in this range. We can, just show that it's so. We can write that in this notation: the union of the sets from A minus delta to A and A to A plus delta, and we can also write it in this inequality notation, where x is between these but it's not equal to A. You can also write it as A minus delta to A, or A to A plus delta. That's fine as well. You can also say that the distance between x and A must be between 0 and delta exclusive. So it can't be 0 and it can't be delta. So then you can write it with absolute value, because absolute value just gives the distance between 2 points, right? So now that we've covered that, we can go on to the definition of a limit. So if I say that the limit of f of x as x approaches A is equal to some limit L, that's the same thing as saying that for all epsilon greater than 0, there exists delta greater than 0, such that if the distance between x and A is between 0 and delta exclusive, and I can choose any delta I want, then I can guarantee or imply that definitely the distance between f of x and the limit will be less than any arbitrary epsilon that's greater than 0. So, for example, let's say I had the function f of x equals x, right? And I wanted to show that the limit of f of x as x approaches 0 equals 0. So what does that mean if you have the function here, right? It means that you can tell me how close you want f of x to be to 0. I can guarantee that f of x will be as close as you want to 0 by making sure x is as close to 0 as I choose, right? So for example, if you tell me I want f of x to be within 0.5 of of 0, and this is of course exclusive, so like f of x will, will not be 0.5 of 0, it'll be less than 0.5 of 0. I can guarantee that by telling you that x should be, well, not should be, if x is um, if x is within 0.5 of what it's approaching, which in this case is 0, then f of x will be within 0.5 of 0. And we can see that because let's say this is 0.5 and this is negative 0.5, right? We're just talking about, these are distances. So they can be negative or positive, right? So this is going to be like 0 plus epsilon, or in this case our epsilon is 0.5. So I'm just going to write 0.5, and this is minus 0.5, right? And this is basically our limit, let's say, right? And then I'm telling you, well, if you pick up any point like here, right? If you pick any x value here in this range, right? So this is like 0 or a minus delta, 0 plus delta. If you pick any x value here, like let's say for example we had f of x equals x when x does not equal 0. Let's say it's a piecewise function and it's equal to, let's say, whatever, it doesn't matter, 10 when x equals 0, right? So then at the actual point 0, it wouldn't actually be equal to 0. It would be like a hole here. It would actually like be over here. It doesn't matter, right? Well, it doesn't matter because we're saying that if x is in this, in here, or in here, then we're guaranteeing that f of x is close to whatever we're saying the limit is, which in this case we have our limit equal to 0. And you can clearly see that in this case, if x is within 0.5 of 0, then f of x will be within 0.5 of 0 as well, right? And in this case, what's cool is you can actually just choose epsilon to be equal to delta, because if you ask me, okay, sorry, you don't choose epsilon. Epsilon can be arbitrary, but you choose delta, so you can choose delta to be equal to epsilon. And what's cool here is that, let's say somebody tells you, I want f of x to be within, I don't know, it doesn't matter, 0.001 of 0. Well, then I can just tell you, okay, to guarantee that, make sure that x is within the same thing. Right, so this is our limit and this is our a, which happen to be the same. They're not always the same. And we can see here that this is going to work because f of x is equal to x, right? Like that's our original function, so when x does not equal 0, right? So we're saying x has to be within 0.001 of 0, but not 0, right? So it is equal, fx equals x when x is not 0. So therefore, if x is within this, then obviously f of x will also be, and in this case our limit is equal to this. So and because in this case we have our limit equal to our a value, these values will be exactly the same as well. let's say for example, if I had f of x equal to x plus 1, then now our limit would just be 1, because f of 0 is 1, right? And when you get close to 0, f of x will be close to 1. And now, yeah, these values will still be the same. You still have delta equals epsilon, because if you're within 0.001 of 1, well, if you're within this distance of 0, then the number that you're adding to 1 is going to be within this distance of 0, so it will be that close to 1, right? Yeah, so that's basically what the definition of a limit is. Yeah, so let's do an example. Let's say I wanted to show that the limit of, let's say, x squared as x approaches 2 equals 4, right? If I want to prove that, first I'll write what we're trying to prove, that for all epsilon there exists delta such that if the distance between x and the value it's approaching is as close as we tell it to be, right, and greater than 0, then we can guarantee that the distance between x squared and 4 is arbitrarily close, right? So let's start with this. So this means this is just a difference of squares inside, right? And what you could notice here is that I have two things that are being multiplied here. When they're going to be multiplied with each other, they're either going to be negative or positive. In terms of like the magnitudes, it will always be the same. And then the absolute will make it positive. So if I write it like this, then we're definitely going to have a positive times a positive. Or if one of them is 0, then the whole thing will be 0 anyway. So this should be the same, right? So we want to get somewhere that looks like this, because then we can decide what we want delta to be. But the problem is that we have this. This is similar to this, but we have the x plus 2 term here. So what we can do is we can restrict delta right now. So remember, we can choose any delta we want that's greater than 0 to make sure that this implication holds. So I can choose that delta is definitely going to be less than or equal to 1, right? You can choose any number here to get rid of the x plus 2 term, but 1 is the convention. So if we have x minus 2 less than delta, which is less than or equal to 1, then it makes sense that x minus 2 will be less than 1, right? And then from here, it makes sense that x minus 2 will be in this range, because basically, in general, why if you have absolute a less than, doesn't matter, some positive number b, that's the same thing as saying that a is in this range. That's because we can rewrite this as like a minus 0, right? So the distance between a and 0 has to be less than b, so obviously that can only be true if a is between negative b and b, because if a was equal to negative b or b, the distance between a and 0 would be exactly b. And if it was any bigger than b or less than negative b, then the distance would be greater. So from that, we can just always change from this form to this form. No, we want to get x plus 2, so we can add 4 to everything, right? And now, because everything is positive, right, we know that for this to be true, for x plus 2 to be greater than 3, this can only be true if x plus 2 is equal to x plus 2, right? So if this is true, that implies that this should also be true, right? That makes sense? We're just being like, if this is true, then this is true, then this is true, then this is true, and this is true, right? So we want to find something that's bigger than x plus 2, which is the 5. The reason why we want to do that is because we want to ensure that epsilon is greater than this, right? And we can do that by saying that, well, if epsilon is greater than x minus 2 times 5, then it must also be greater than x minus 2 times x plus 2, because 5 is bigger than x plus 2, right? Yeah. So this would kind of make sense, that if epsilon is bigger than this, it would also be bigger than this, which is what we're trying to make sure, right? Because that's what we're sort of telling, we're trying to make sure is true here. So then from here we have this, so then we just have x minus 2 less than epsilon over 5. But we know that x minus 2 is less than, we know that x minus 2 is less than epsilon, so then if epsilon were equal to epsilon over 5, this would, right, that would work, right? And we know that epsilon's positive, so we know that a positive number divided by 5 is still going to be positive, so that's good. But the only thing is, we made this assumption here. It is possible that epsilon over 5 will be greater than 1, but we said it has to be less than or equal to 1, so I'm gonna just say that it has to be the minimum of this and 1, right? So that way, if epsilon over 5 is bigger than 1, epsilon will be 1. If it's equal to 1, if epsilon over 5 is greater than 1, delta will be 1. If epsilon over 5 equals 1, delta will be 1. If epsilon over 5 is less than 1, delta will be epsilon over 5. So we're gonna guess. I mean, we're saying guess, but we know this is gonna work because we kind of just proved it, but we want to make a more formal proof. So the way that's done is we say what we're given, which is this for all epsilon. So no matter what epsilon greater than 0, this has to work. So we're given epsilon greater than 0. We can choose any delta we want because we're just saying there exists, so there's at least one delta. So we just have to find one delta that works for all epsilon. So that can be the minimum of epsilon over 5 and 1. Then we want to suppose that that this is true, right? We're supposing that 0 is less than x minus 2, which is less than delta. Now, in this case, this is kind of redundant because even if the distance is 0, then you're just going to have, if the distance is 0 between x and 2, then you're just going to have 4 equals 4. So for all epsilon greater than 0, that's going to be fine. But whatever, we can leave it for now. But this is the main part we're concerned with. Then we want to show that uh, this, right? What we're trying to imply, that we can be within epsilon of 4. Sorry. Yeah, we can be within epsilon of 4. The function will be within epsilon of 4. So, right. So we're going to start with our supposition that, right? So actually, first of all, I'm going to split this into cases. The first case is that delta equals 1. That means that for this function to have returned 1, it means that epsilon over 5 must have been greater than 1. Yeah. Which is, or equal, right? Then these are the two, either it's greater or equal to 1, then the minimum function will return 1. And this is equal to delta, which, this is where our supposition comes in. It's greater than x minus 2. So this means that this is bigger than this. Which means that this is bigger than, multiply both sides by 5. And we showed how when delta is less than or equal to 1, which it obviously is here, then we know that 5 is bigger than x plus 2. Right. Yeah. That's it. And if we have the case where delta equals epsilon over 5, that means we know by our supposition that x minus 2 is less than delta epsilon over 5. And then that's exactly what we have here. So we can say, like, by steps, by implications, from 1, we have that epsilon should be greater than x squared minus 4. And that's it. That's the proof. So that's basically the gist of definition of a limit and delta epsilon proofs. So our next thing is continuity at a point. So a function is continuous at a point, let's say f of x is continuous at x equals a. If, and only if, I guess you could say, limit of f of x as x approaches a exists, f of a exists, and by exists I mean, like, it has to be not infinity, and has to be, like, defined, right? Yeah. And then the last condition is that these have to be equal to each other. So this is the main thing, because for this equation to even make sense, then f of a should have to exist, and the limit of f of x approaches a has to exist. It's impossible for a function to actually be equal to infinity. So for this to be true, f of a can't be infinity. So this doesn't even matter when you write the statement. And if they're not if this isn't defined, then a limit can not exist, but like it's not the same thing as defined, right? Basically, if you can solve this and get some value of a, right? Then at that value of a, f of x continues. And if this is true for all values of a on f's domain, then f of x is continuous on its domain. And also, well, if it's like for all real numbers, if it has a domain that's like this, like an open interval domain, then this is fine too. But the only place where you have problems is maybe you have a domain that's like this, or just either this is closed, or both are closed. So when you have closed intervals, you have to deal with side limits. So for this to be continuous, this would have to be true for all points on this interval. But also, f of, for all, let's say, for all a in this interval, but then also, to make this less confusing, let's call this like this. Just give them some sign. F of a1 needs to be equal to the limit of f of x as x approaches a1 from the right. Because obviously if f of x is not defined on the left of a1, then it's not, the limit will not exist for the limit of f of x approaches a1. So that's continuity on an interval. I mean, I can show a quick example. Let's say I wanted to show for let's just say I want to show for f of x equals x is continuous over all real numbers. So this is also its domain. I have to show that f of, just copying from here, right? F of x, f of a should be equal to the limit of f of x, which is just x in this case. I'll just write x as x approaches a. And f of a is just a, right? And this is a common rule for limits. This is, I think it's called the identity limit law. I can check that. Identity limit law. No. Direct substitution law. Okay, direct substitution law. No, identity function. Oh, identity function. Okay. Identity function. So, yeah, this is called identity function law. I can prove it quickly. It's just what we said before. for all epsilon greater than 0 because delta greater than 0, such that if we have, well, in this case, we don't even need the 0, right? Because if x equals a, then you just have that the difference between a and a is 0, so for all epsilon greater than 0, a will be with an epsilon of a, so we don't even have to worry about the 0. We can just focus on this part. And if x is within a of epsilon, sorry, if x is within delta of a, then it should follow that oh, this is funny. You just get this because in this case our f of x is the same as our x, and our limit is the same as our as the value we're approaching. So that's pretty funny. This has to imply this. Well, obviously, if we can just choose delta to equal epsilon, which we're given epsilon greater than 0, so that's greater than 0 as well, then obviously x minus a less than epsilon implies that x minus a less than epsilon, right? So that's pretty easy to see. Okay, so that's sort of the delta epsilon part of the course. Now I'll just go over curve sketching and optimization, and that will be the end of the review. So let's try and sketch the graph x squared plus 1 over x. So the first thing we can look for is the domain. This is defined everywhere where x is not 0, obviously, because this is polynomial. It's going to give you a real number. This is going to give you a real number. This is always greater than, well, it doesn't even matter. This is the numerator. The only way where a real number over a real number is not going to give you a real number is where you're dividing by 0. So our domain is just going to be like this. Now we can look at our range, although that might be a little bit difficult, so we can leave that. The range isn't very important. We can look at x-intercepts and y-intercepts. So y-intercept is f of 0, which is not undefined. It's division by 0. This is going to be 1 over 0, right? If we do f of x equals 0, then this can only happen if the numerator is 0. Because if the numerator is not 0, then you can't divide it by anything to make it 0. So we need x squared plus 1 to equal 0. But again, this can never be because you'd need x squared to be negative. Or if you think of a graph, like obviously this is always greater than 0, so it's never equal to 0. Yeah, so we have no intercept. The next thing we can look for is symmetry. This clearly has no symmetry because this is like even power, this is odd power, so it's not going to be an even or odd function. If you want to show it quickly, we can just show it like f of negative x is going to be x squared plus 1 over x, but like negative, right? Because the x will be negative, and the numerator will be exactly the same, because the numerator is an even function, right? And then negative f of negative x is just going to be it's going to be negative this. Oh, I guess the function is odd then. Really? it looks like our function is odd. Looks like it. Okay, I guess we have an odd function. Cool. So, forget what I said before about this function not being odd. uh, because f of x equals negative f of negative x means that f is odd. So that means that we have point symmetry about the origin. Yeah. Which makes sense because I guess whenever you have an odd function like 1 over x times an even function, you should always have, I guess, because when you plug in negative x, the even function will remain unchanged, and this will flip. But then you do negative f of negative x, will flip. This will be like the odd function will be negative, because you can rewrite an odd function as negative f of x equals f of negative x, and then it's going to reflip it. So yeah, I guess whenever you have an even function times an odd function, if you it should just be an odd function. Odd function times even function should be odd function, I believe. Yeah, we can try and prove that quickly. If you have, let's say, f is odd and g is even, so g. So let's put the negative on this side. Like this. And then if you have f times g, then we know that, let's say this is some function h. Negative h of negative x is equal to negative f of negative x g. Yeah, f of negative x, g of negative x. We know that f of x, sorry, well, if we want, we can put this back here. F of negative x is negative f of x. And g of negative x is g of x. Delete the minuses. Wait, what? Negative, sorry, what am I doing? F of x equals negative f of negative x. So, sorry. This negative f of negative x is equal to f of x. And this is h of x. So, yeah, h of x is going to be an odd function. Okay, so that's cool. Yeah, nice. So we have point symmetry about the origin. Okay, next. We can look for asymptotes. Obviously, there's going to be when x equals 0. Also, we can look for an oblique asymptote. In this case, because the degree of the numerator is greater than the degree of the denominator, we should have an oblique asymptote. So we have x squared plus 1 over x. We can do long division here to find what the oblique asymptote should be. So we know that x, we want to find what times this will give me this, so that would be x, right? Let's also rewrite this. like this. In general, you want to have like all the powers of x up to the power that you, up to the last power. So if you don't have one of the powers, then just add a 0. So we wanted to have an x, x times x squared. Yeah. We can now subtract this. So you just get a 1, right? Or, yeah, you get a 1. So therefore we can actually, this, we didn't have to go through this trouble. I just realized now we could have just written this as x plus 1 over x to start with, just by splitting this up into x squared over x plus 1 over x. But whatever. Yeah. I think it's pretty clear that when x approaches infinity, 1 over x will approach 0, so really this is the only thing that matters. So that means that x squared over x will approach x when x approaches infinity. So our oblique asymptote is just y equals x. And this was our horizontal asymptote. Sorry. This was our vertical asymptote. Okay. I guess the next thing I would do is find critical points and points of inflection. So to do that, you have to differentiate. I think like even this could be really easy to differentiate instead of differentiating this. So yeah, it's just gonna be this. To differentiate this, you could just write it as x to the minus 1, use the power rule. This decreases by 1, this is just 1 over x squared, so you got minus 1 over x squared. This is our first derivative. And our second derivative will just be the 1 becomes 0, right? This should just be two over x cubed. Yeah. So we want to see where the derivative and second derivative either don't exist or equal 0. So they both don't exist when x equals 0, but that's not in the domain of our original function, so they're not really critical points or possible points of inflection. But we can look for when it equals 0. Yeah. Okay, these are our critical points. Just bring this to the other side, multiply both sides by x squared, and just take plus. Whenever you have this, if you really wanted, you could write it like this. And it's a difference of squares. And then the solutions are just 1 and negative 1, or negative 1 and 1. But when you have, in general, for x squared to be equal to any value a, then either x has to be equal to root a or negative root a. Those are the only two ways that it could possibly be. If it's, yeah. So yeah, those are critical points. And then if we have this equal to 0, well, this obviously has no solutions, because for this to be true, then 2 would have to be equal to 0, which it's not, so there are no points of inflection. And also, this is always, there are no points of inflection, but the asymptote, it will change concavity before and after the asymptote the function, so we still have to keep this in mind. So if we have our table here of our derivative and our second derivative, and we can draw a quick sketch of our function. So our derivative, so we want to have, there are no x-intercepts, we would put those here. We want to have, we start at negative infinity. We want to have our critical point, and we want to have our, critical points and our vertical asymptotes. So our asymptote was 0, so we're going to have our critical point, our asymptote, vertical asymptote. We don't put horizontal asymptotes on the sign charts. Another critical point, and infinity. So our first derivative was this function. So if you have a number here that's very negative, like negative 10, then the x squared is going to be very big, so this is going to be about 0, so it's definitely going to be positive, right? Same thing here. Alright, it is an odd function, so if I plug in points, so like, yeah, this is going to be the same as this, and this will be the same as this. So if you plug in a point like close to 0, then this is going to be big. Sorry, this is going to be small. So this is going to be big, so it's going to be negative, right? If you square a small number, then it's still going to be small. And then you divide 1 by that, it's going to be big. So yeah, and this is always going to be positive, so this is going to be positive and big, so 1 minus that. So this is our first derivative. This means that's increasing, decreasing, decreasing, increasing our function in these intervals. For a second derivative, it's pretty simple. It's just going to be like this. Yeah. Which does make sense. So, yeah, this makes sense. Yeah. For an odd function, if it's concave up on one side, then when you rotate it, it should be concave. It should be the opposite on the other side. So then the function will be increasing and concave down. That looks something like this. Here it'll be decreasing and still concave down. Looks like this. Here it will be decreasing concave up. That looks like this. Here will be increasing concave up. That looks like this. Okay. Now we just have to do a quick sketch. So we have our asymptote here at x equals 0. This is y, this is x. We know that we have our, so we see that it's going to look like this, and it's going to look like this. Just copying these two here and here. We know that we have our oblique asymptote at y equals x. And yeah, that's basically it. We're done. Oh, our critical points are negative 1 and 1, so it's gonna be our, well, clearly this is gonna be a maximum, this is gonna be a minimum, local max, local min, right? So it's going to be over here and over here. And if we wanted to find the value of these points, we could find them pretty easily just plugging it into the original f of x, which was, I believe, x squared plus 1 over x, right? Yeah. So instead of just writing f of x, you can write okay. And yeah, we can, if you put in 1, you get 2. If you put in -1, well, obviously it's going to be negative, like -2, but based on if we have f of x equals negative f of negative x, then f of 1 should equal negative f of -1. So f of -1 should equal negative f of 1. This we said is 2, so it should be -2. And just to confirm, if you put in, oh my god, why did I change this to be, oh, this is the derivative. Oh my god, no, what? I'm confusing myself. Oh yeah, it is -2. Yeah, because it's just -1 squared is 1, and the x is -1, so you get 2 over -1 is -2. Yeah, that makes sense. So yeah, that is the curve sketch. Can confirm it's right here. Yeah, looks pretty good. We can see that our points here are right. 1, 2, -1, -2. Cool. If you want, we can label them. Doesn't really matter. And yeah, so that's curve sketching. And the last thing I wanted to cover was optimization. Show that the area of R is maximized when b equals 2a. So we know that the area in terms of a and b is equal to ab. We know that the perimeter in terms of a and b is equal to 2a plus b. We also know that the perimeter will be some constant value. Let's call it p. Let's say that is our perimeter. It's just a constant value. We can isolate for either of the variables, but let's isolate for b. Doesn't matter. We can plug this into the area formula. So now we have the area just in terms of a. Since p is a constant, it's not a parameter. It's just going to be like this. So can just write this as pa minus 2a squared. We can find the derivative now. I mean, yeah. Okay. Well, I mean, if you really wanted to, you could write this. You can factor out the a and get p minus 2a. And if we sketch this graph, this is like minus 2a plus b. Then we're going to have a root at 0 and a root at negative p over -2, right? If we set this factor equal to 0, then you get A equals negative p over negative 2. That's just p over 2. And we know that p is positive. The perimeter has to be positive. Because a and b both have to be positive. If you say that one of them can be 0, then but yeah, the perimeter is 2a plus b. I don't know. It doesn't make sense for the perimeter to be 0. So let's say the perimeter has to be positive, which means if the perimeter is positive, you can't have negative a or b. That doesn't make sense. That means that at least one of them has to be positive. Yeah. If one of them is 0, then the area will be 0 anyway, so obviously you're not maximizing it. So we can just say that a has to be greater than 0 and b has to be greater than 0. I think that's a reasonable assumption. So if you have a equals p over 2, that's going to be, let's say, here. And we know that the maximum will happen right in the middle because it's just a quadratic equation. So that's going to be p over 4. So our maximum area will occur when it will happen sorry. This is our area in terms of a, right? So the maximum area will occur when a equals p over 4. So this is a way to do it without calculus. So if a equals p over 4 and b equals p minus 2a, that's p over 2. So b equals p over 2. So we see that b is going to be twice the value of a, which is what we wanted to show. But if you wanted to use calculus, that's not a problem either. We could just find the maximum of this using derivative. Use the power rule. So this is 1, then this becomes 0. It's 0 just 1, so it goes away. This comes here, we get 4. Power goes down to 1. I want to set this equal to 0. So first of all, we can see that never mind. First, let's set it equal to 0. Then you get a equals p over 4. Just put this here, and then divide both sides by 4, right? Add 4a on both sides first. And then, yeah, to show that this is a maximum and not a minimum, we can show that, well, we can just use a chart. We know a rate will range from 0 to infinity, so and our initial thing was just a times p minus 2a. So if you put like I don't know, p over 8, then this is p over 4, so this is 3p over 4, right? We're putting in p over 8. A is p over 8. Multiply these together, you get 3p over 24. That's just p over 8. If you plug in p over 4, then 2 times p over 4 is p over 2, so this is p over 2. That's just p over 16. Sorry, p over 8. I must have made a mistake here. A is p over 8. P over 8 is 2 times that's p over 4. Should be 3p over 4. I see. This is 32. Okay. So clearly A is increasing, right? Yeah. Well, I mean, if we allow A to be 0, right? If, like, I guess in theory you could have A be 0, and then just B would equal the perimeter, which would be greater or equal, which would be greater than 0. Then, I guess in that case we wouldn't even have to do a chart. We could just say that. We could just check the end point. Well, there's no end points. Sorry, never mind. We have to do a chart. What I wanted to say is we want to check when is this positive or negative. A prime is, if we want to check when it's greater than 0, then you have for A greater than 0, so add 4A on both sides. A is less than P over 4. So when A is less than P over 4, it's increasing. And then you have this. Then you get P over 4 less than 0 by the same steps as here. So when, sorry, not 0, A. When A is greater than P over 4, it's decreasing, so clearly we have a maximum. Yeah, it doesn't even matter even if this went to negative infinity, but it doesn't, right? But yeah, we clearly have our maximum here when A equals P over 4. And yeah, we see that our maximum area is P over 8. And that A is P over 4, and B will be equal to P minus 2A, which is P over 2, because 2A equals this, so B will equal P over 2, and clearly this means that if we want to say that B equals some multiple of A, and B equals P over 2, and A equals P over 4, can divide both sides by P, multiply both sides by 4, K equals 2, B equals 2A, which is what we want to show. So thank you for watching my review, and see you next time.